So in the last screencast, I did one example of a projectile motion problem for you. But if you'd like to see one more to see some of the variations on these types of problems, I'll show you another kind of problem we can solve, again, using the same concepts and ideas that we talked about on projectile motion. This one has a rescue plane that's going to be dropping off a set of supplies to a stranded party. So here's the rescue plane. It's going to drop out these supplies to some people that are maybe down here, and they're like in the middle of the forest. And what we want to find out is basically if we have this plane at 100 meters in altitude and flying at a constant velocity of 40 meters per second perfectly horizontally, we want to know where are these supplies going to land. Essentially, this would tell us where should the plane drop the supplies in order to have them land at the stranded party. Now, in this case, we notice that this is not something where we are launching an object at some sort of angle to the ground. In fact, we're at essentially a 0-degree angle, or we're launching horizontally. And we want to find out where is this going to land? What is this x value that we're going to be solving for? Now, what I want you to notice is that if we're looking for an x direction thing, there's really only one equation in the x direction, and it's that constant velocity in the x direction multiplied by a time. Again, there's no acceleration in the x direction, so this one equation works for everything x, essentially. In this case, we do want to know this x variable. We do know the initial velocity in the x direction because, again, whatever velocity it was traveling with initially, or that 40 meters per second, it's going to maintain that velocity the entire time in the x direction. So this thing also has a value of 40 meters per second in x. The problem is that we don't know the time that it's going to spend in the air. If I could figure out that time, now I could use this simple equation and find the value of x. So we do need to go to our y direction in order to figure out where this thing, or how long this thing is going to spend in the air. So in my y direction, I can plug in some of the values that I know into this equation here. Now the change in position in the y direction, which I could write as y sub f minus y sub I, or just a delta y, is going to be this negative 100 meters because the supplies are going to start 100 meters above ground and then drop down to the ground level. The initial velocity in the y direction, again, if we look at this vector here, we can see that none of it is in the y direction. So that's just simply going to be a 0. The acceleration in y, of course, is our negative 9.8, so half of that is going to be negative 4.9 t squared. If you want to pause the video and try finding that t value yourself, go ahead and do that. Solving for t, you get about 4.52 seconds. Now that we know how much time the object spends in the air, it's very simple to come up to this x direction equation, plug in our velocity in the x direction of 40, plug in our time of 4.52 seconds, and we'd find that this object would land about 181 meters away from the drop point.